Hello, everyone. Today we're going to be discussing limits and continuity. That's basically your unit 1. Now, in grade 12 calculus in particular, you don't really have to understand what limits are mathematically. You kind of have to realize what they are graphically, and then you have to be able to evaluate them. In reality, limits are complicated mathematical definition. We'll get to that at a different time when we start talking about the actual like formal definition of limits. But for now, here's how I'm going to define it. Let's say you have a graph and your graph does something like this. And let's call this point A. Let's call this L1. Let's call this L2. And let me extend this thing a little bit. And let's call that one L3. And this is your function y equals f of x. So there are two different ways that if you're a person on the x-axis can approach A. You can approach A from the left side, or you can approach it from the right side. Now, the goal of limit is this. If I approach point A on the x-axis from the left side, and I keep looking up at my function, right? So imagine if this person is looking up. And I keep looking up at my function, what are the y values getting closer and closer to? So here, I look at my y value, my y value is here. Here, I look at my y value, and it's here. The closer and closer I get to A, the closer my y values get to L1. When I'm here, it looks like here. You see your values are getting closer and closer to L1. Now, what's important for you to realize is that L1 is actually not the value of the function at point A. That's L2. So f of A is actually equal to L2. So the limit when you approach, or the value of the function when you approach A from the left side, doesn't really have much to do with the value of the function. It has to do with what value you're approaching. Now, how do we put this concept in a more compact form? We use limits. So we say the limit of our function f of x as x approaches a minus. What does this a minus mean? It means it's approaching A from the left side. So it basically means it's approaching A from values that are less than A. A minus means less than A. And we just showed that it is equal to L1. So as you get closer and closer to A, what are your y values getting closer and closer to? Which the answer would be L1. Now you will have something very similar to this on the right side. So as you approach A from the right side, as this person on the x-axis gets closer and closer to A from the right side, what are your y values getting closer and closer to? You see that that value is L3. So we say the limit of f of x as x approaches A plus is equal to L3. Again, none of these values are necessarily equal to each other. We will see later on that if they are equal to each other, continuity is met. So if your limit from left and right and the value of the function at that point are the same, your function is continuous. That's actually called the condition of continuity. So this is the definition of one-sided limits. People call these one-sided limits. Now, if these two are not equal to each other, so if you have a point and you approach that point from the left and you approach that point from the right, and you don't get the same value, then we say that the limit at that point does not exist. So if the limit of f of x as x approaches a minus is not equal to the limit of f of x as x approaches a plus, then we say the limit of f of x as x approaches a does not exist. On the other hand, if they are equal, then, and let's say they're equal to number L, then we just say that the limit of f of x as x approaches a is equal to L. So if from both sides you don't get the same limit, just the limit doesn't exist. If you do get the same limit, then the limit is just equal to that number. Again, keep in mind that this does not have to be the value of the function at all. So this is the general idea of limits and what they're used for. If it's as you're approaching a point, what y value are you approaching? Okay, now how do you evaluate these algebraically? It's very simple. The first thing you always do, the first step that you always have, is you should plug it in. So always try plugging in the a or a into your function. If nothing weird happens, and we're going to talk about what I mean by this, what is this weird thing that we're talking about, then that's your limit. You have it. So just as an example, let's say I want to know what's the limit as limit of 3x plus 4 as x approaches minus 2. The first step in your mind, no matter how complicated the limit looks, is or should be plugging in the number in here. It would be 3 times minus 2 plus 4, which is minus 6 plus 4, which is minus 2, which is nothing weird. We get, but let's say instead you have something like this. You have the limit of 3x minus 6 over 2x minus 4 as x approaches 2. Well, the weird thing that happens is if you plug in 2 in here, you see 3 times 2 minus 6 over 2 times 2 minus 4, which just gives you 0 over 0. That's something weird. That's something that should not happen in math. You should not have 0 over 0. You might be tempted to say that this is infinity, but in fact, we treat 0 over 0 very differently in limits. The reason for it is actually not that complicated because you don't really get to 2 in this function. So if you actually draw this function, you will see that you have a hole at 2. So plugging in 2 in here will give you an answer that doesn't really exist. But 0 over 0 in general is a weird case. It's one of the weird cases that you deal with. So your first step always should be plugging in the number. Do that first, and then you can deal with the consequences after. Okay, now let's see what are these weird cases. So we have 0 over 0. That's one of the stuff that we had here. We also have plus minus infinity over plus minus infinity. These are the weird cases that you're going to deal with in Unit 1 type questions. Now, there are some stuff that might look weird, but in fact, they're not weird. So, weird looking cases that are not weird. Their answers are already like determined. Weird looking cases that are not weird. any number, I'll just write it as that, divided by positive or negative infinity. So let's say you plug in a number into your fraction, and on the top you get a number, and at the bottom you get plus minus infinity. This is always equal to 0. The analogy I give for this is if you have like 4 different cookies and you divide it between 1 million people, the result is going to be everyone is going to get a crumb, right? People are not going to get much of a cookie at all. The other one is what happens when you have a number and it's divided by, well, we say 0, but it's in fact not 0. It's generally 0 plus or minus. So that means a very tiny number at the bottom, or 0. So a number divided by 0, limiting 0 basically. This is a case where you have positive or negative infinity, depending on the sign of these two. So if the number up top is positive and the 0 is negative, it means you have a tiny negative number at the bottom. The result would be positive over negative would be negative infinity. So this sign has to be determined using the sign of the number and the sign of the limiting 0 at the bottom. Well, the analogy for this one is if you have a number of cookies and you're gonna, so if you have one cookie, let's say, and you want to divide it between like 2 ants, each ant is gonna get a lot of cookies, right? So a large sum divided by a very limited number of people is going to be infinity. Yeah, so these cases look weird, but they're not really weird. Oh, also these weird cases have a mathematical name. They're called indeterminate forms. And we need to be able to deal with those. So we kind of have our weird looking cases that we know what to do about. We have our cases that are not weird. You just get a number and you're good. So the only real case that's left for us to deal with are these weird cases. Now, let's talk about 0 over 0. I'll talk about infinity over infinity after. So 0 over 0. There are 3 different possibilities when you have a 0 over 0 case. Possibility number 1. You can factorize the top and bottom of the fraction and simplify the factored form. So a very easy example of this is what I just gave you. So I told you that it's the limit of x approaching 2. I think I have it here. Yeah, x approaching 2 of 3x minus 6 over 2x minus 4, right? So what can I factor from the top? Well, I can factor 3. So it's the limit as x approaches 2 of 3 times x minus 2. Same for the bottom, I can factorize the 2 times x minus 2. So you see what happens is the x minus 2 and the x minus 2 cancel out. And I can do that because I'm not really canceling out a 0. I'm approaching 2, but I'm not exactly at 2. I'm slightly before or after 2, right? So these x minus 2 and x minus 2 are really, really tiny numbers, but they're not exactly 0. So you just get 3 over 2. Because you basically are left with limit as x approaches 2 of 3 over 2, which is just 3 over 2, right? If you plug in the x in here, you just get 3 over 2. You don't have an x. It's not dependent on x. Just in general, the limit of a constant is just going to be equal to that constant. So that's the number one way you can do this, by factorizing both top and bottom and then simplifying the factored form. The second way is by multiplying by conjugate. So where is this used? When is this used? Well, it's used when you generally have a root. So used are cases involving square roots. So to just give an example on this, you have, let's say, limit of square root of x minus 2 over x minus 4 as x approaches 4. Your first step, as always, should be just plugging in the x equal 4 in there. And you'll see that you have root 4 minus 2 over 4 minus 4. And that gives you a 0 over 0, right? So this is a case that we need to deal with. Now, what do I do here? What I'm going to do is I'm going to multiply the top by the conjugate. So what is the conjugate? The conjugate is basically the exact same thing, just with the negative sign in the middle. So it would be root x just plus 2. Now, remember that in a fraction, if you're multiplying the top of the fraction by something, you also need to multiply the bottom of that fraction by the same thing. Otherwise, you're changing the fraction and that destroys the entire question. Now, what are we going to be left with? Up top, you can just use the difference of squares formula. So you have a minus b times a plus b. That's going to be a squared minus b squared. So I'm going to do the same there. So it would be the first one squared, which is x, minus the second one squared, which is 4. And then at the bottom, you're going to have x minus 4 multiplied by square root of x plus 2. Now you can see that the 0 over 0 is kind of simplifying out. So both your zeros up top and at the bottom are canceling each other out. Now you can just plug in the 4. So it becomes 1 over root 4 plus 2, which is 1 over 4. And then the last case are the variety cases. So variety cases. These cases themselves can be broken down to multiple categories. One of them is just involves simplifying examples. We're going to spend some more time discussing examples in a video that I'm going to upload next week. But in simplifying examples, you're going to get complicated statements, like complicated algebraic expressions up top and at the bottom. And then when you simplify those complicated statements, or again, expressions, you can simplify them. And that gets rid of the 0 over 0. The other one is basically simplified, but using algebraic identities. And two of the very important algebraic identities that you have to carry with yourself all throughout this course are difference of cubes and sum of cubes. So you have a cubed minus b cubed. This is a minus b times a squared plus ab plus b squared. And then you also have a cubed plus b cubed, which is a plus b times a squared minus ab plus b squared. So in grade 12 calculus, these are the different types of 0 over 0 cases that you would encounter and you have to be able to deal with. We're going to get, I'm going to dedicate a video just discussing how to solve questions using these two. And then the last thing really left for us to discuss with evaluation is the plus or minus infinity over plus or minus infinity. The good news is this case, you don't need to know all these three different things. The one piece of advice I give you for these cases is, number one, heavily suggest factoring out the highest, power of x from both top and bottom. And then 2, I suggest remembering that 1 divided by, or not 1, any number divided by positive or negative infinity would go to 0. So you can basically get rid of that in your solution. Because when you end up factoring out the highest power of x up top and at the bottom, then you end up getting fractions that you can just cancel out. I'll give you an example of this one. This one is simple enough that we can just fit an example in this video. Let's say you have the limit as x approaches to positive infinity, 3x squared plus 4x minus 7, and then 2x squared minus 6x plus 3. So first things first, if you plug in infinity in here, you just get 3 times infinity squared, which is infinity, plus 4 times infinity, which is still infinity. And when it's minus from 7 up top, you just end up getting infinity. And if you plug in infinity at the bottom, you still get infinity because you have 2x squared, which is the dominating term, and that dominates everything else. So you just get infinity over infinity by plugging in x. But with my suggestion, what you're going to do is you're going to factorize the highest power of x at the top. What's the highest power of x at the top? It's x squared. So you're going to factor that out. It becomes x squared times, when you factorize the x squared, you have to divide everything by x squared inside the brackets. So 3x squared over x squared, that's a 3, plus 4x over x squared, that gives you 4 over x, and then minus 7 over x squared. So that's how factorization works, right? When you factor something out, you have to divide everything by that factor. So 3 plus 4 over x minus 7 over x squared. Same for the bottom. I'm going to factorize the x squared, so it becomes 2 minus 6 over x plus 3 over x squared. And hey, look, you have a bunch of numbers divided by infinities, because as x goes towards infinity, this one goes away, this one also goes away, this one goes away, this one goes away. And in other good news, x squared and x squared cancel each other out. So what you're really left with is the limit as x goes towards infinity of 3 over 2. And you know how to deal with that, as like the limit of a constant number is just going to be 3 over 2. Okay. I don't want this video to run too long. This is mostly going to be about concepts. We're going to do some questions in an upcoming video. But what I do want to touch on is the idea of continuity. So we need to first talk about what it means for a function to be continuous. Well, that's a topological problem, really, and it's pretty difficult to actually discuss it. For those of you who are interested in math, topology is probably going to be your end, because it's by far one of the most difficult parts of math. And it is difficult to actually define what it means for a function to be continuous. But for now, we're just going to say a function whose graph can be sketched without lifting your pen off the paper. So what does that mean? That means something like this is continuous. However, something like this, the example that I gave you guys before, that's definitely not continuous. And it's not continuous at that point in the middle. So continuity is a point by point idea, right? It's continuous everywhere else. It's just not continuous at that point in the middle. Now, how do we know that a function is continuous? Well, that's easy. You have this condition for continuity. So for a function to be continuous at x equal a, so at one point, the limit of your function as x approaches a needs to be equal to the value of the function at point A. Now, keep in mind that that means two things, right? That statement actually has two inner meanings. The first part, the limit as x approaches a of f of x is equal to f of a, that's telling you that the limit has to exist. So as you approach from the left side and the right side, you have to have the same limit, and that needs to be equal to f of a. If either of those two things are not met, your function is not going to be continuous. So there are two ways this can break. Either limit of fx as x approaches a plus is not going to be equal to the limit of fx as x approaches a minus, right? And this can cause discontinuity, or the limit of fx as x approaches a plus is actually equal to the limit of fx as x approaches a minus. So the limit does exist. It's just the problem is that it's not equal to f of a. And I can show you examples of either of these. So in this one, you have something like this. You have something like this. So here, the limit from the right side is actually equal to the value of the function, but the limit from the left side and the limit from the right side are not matching, right? This is what we call a jump discontinuity. Whereas what we're talking about here, you might possibly have a hole. Like from both sides of the function, as you're approaching that point A, you have the same, you basically have the same limit, but you're not going to have the same value of the function, right? So both of those can create discontinuities in different ways. In the next video, we're going to discuss a bunch of questions. And yeah, if this was helpful, please like and subscribe. And I will see you in another video. Bye-bye.